everybody, I'm Taal.
And I'm Small.
And today we are doing Khan Academy's MCAT Prep Biomolecules Carbohydrate questions. Learn about some carbohydrates. Okay, first question. Imagine that samples of each of the following carbohydrates were given a +1 charge through bombardment. Oh, I love saying that word and watching it be read out. Okay, cool. Through bombardment with electrons, and then put through a mass spectrometer. Which carbohydrate molecule would you predict to have the smallest measured deflection? Is it glucose, sucrose, mannose, or galactose?
Do you remember the overall idea behind mass spec and how it measures sizes?
So the smaller things go further?
Yes.
Okay, smaller things go further. So the +1 charge, is that just what it needs?
Well, see, I don't know. Do the smaller things go further? Because I thought for some reason maybe the larger things would have more momentum.
Ooh, you could be right. Dang, this hinges on us getting a binary question right.
Yeah.
Well, okay, so let's look at these answers real quick. So glucose versus sucrose, mannose, galactose. Are any of these 5 carbons?
So my mind just blanked. So glucose and galactose are both 6-carbon isomers.
Right.
Sucrose is a disaccharide, so it is connected. Fructose and glucose, I think. And I can't quite remember what mannose is.
In my head, I was thinking mannose was a 5-carbon sugar. So, assuming I'm right, we have a 5-carbon sugar and a disaccharide.
Right.
So once again, we're brought to, does the smaller one or the larger one go further?
You go small and I'll go tall this time.
Ooh, okay, and let's check.
Yay!
Oh, okay, so small was right. It was sucrose, but let's look at those hints to figure out why. Since all the carbohydrates are stipulated to have a +1 charge, the heaviest carbohydrate will deflect the least in the mass spectrometer. Mannose and galactose are epimers of glucose. Okay, I was wrong. Mannose is 6-carbon. They have the same molecular formula. Sucrose is a disaccharide of fructose and glucose. Good job, Small. And sucrose would have the smallest measured deflection.
Well, that's what you said.
Because it's the heaviest, it would not go the furthest.
Yeah.
Oh.
So that is what you said. We just...
Wait, so why did I pick mannose? If I thought that it was the smallest. Because it says, smallest measured deflection. Huh. I think y'all just caught me I just made up my own question in my head and I answered it. Which actually, that happens in the MCAT a lot.
Yeah.
You read the questions, you think about the topic, and you end up just answering a question that you think is actually the question. Question here was, which molecule has the smallest measured deflection? And if we knew that the bigger the molecule, the heavier the molecule, the less far it's going to go, it'd be a smaller deflection. Okay, so next question. Which of the following describes the relationship between the straight chain forms of D-glucose and D-galactose, given that they are non-cyclic molecules that differ in stereochemical configuration at the 4th carbon?
Yep.
So D-glucose and D-galactose, straight chain forms. So what's the relationship between them? Okay, they are anomers, they are enantiomers, they are mesocompounds, or they're epimers. If they differ at 1 carbon, then I don't think they're mesocompounds.
Nope.
Or at least both of them aren't. If it's 1 carbon... Is that so? Enantiomers are non-superimposable mirror images.
Yeah,
and
like the exact opposite.
And diastereomers are non-superimposable non-mirror images. But anomers, isn't that where it's affected at just 1 carbon?
Yeah, anomeric carb. But the anomeric carbon is the one that becomes chiral when the carb forms a cyclic form.
Oh.
Yeah, and I think the previous question gave us epimer. We know that glucose is DLDD,
Mm-hmm.
and the galactose would be Is it DLLD?
I don't know.
Yeah, I think it's DLLD.
Oh, there was a way to remember this.
There's a finger trick.
Like up D L, or sorry, D is right.
Yeah.
On a Fisher projection, L is left on a Fisher projection.
Yeah.
Okay. So I guess I would say that they're enantiomers of each other.
So they are epimers, but let's look at they're stereoisomers that differ in stereochemical configuration only at one stereocenter.
Oh, so epimers is one. I was thinking anomers, but anomers are epimers, but at the anomeric carbon.
Yeah.
Like L and D, those are anomers of each other.
Yep.
Okay. So enantiomers are paramolecules that are mirror images of each other. Anomers are epimers that are in their cyclic state. Okay. And then the straight chain forms of D-glucose and D-galactose are epimers. Okay, so
what if it had said, I'm sorry, epimer versus diastereomer?
Epimer versus diastereomer. I think an epimer could be a diastereomer, but not all diastereomers are epimers.
Okay.
Because diastereomer means non-superimposable, non-mirror image, which would include epimers, but it could be different in two locations on the straight chain, making it not an epimer anymore.
Okay. Oh, so epimer is more specific.
Yes.
I like it. We're going back to the square and the rectangle.
Yes.
They didn't even mention mesocompounds.
Yeah. That one was out pretty quick. Okay, next question. Which of the following molecules is a furanose in its cyclical form? Lactose, fructose, mannose, or sucrose? Furanose. Doesn't that mean it's a 5-membered ring?
Furan, yes. And there's like an oxygen at the top, and then pyranose would be the 6.
Okay.
Or do I have it backwards?
No, I think you're right. I remember in organic chemistry 2 when we had to do the molecule identification thing.
Yeah.
I had a furan, or it was a
THF, right? Tetrahydrofluoran, furan.
Ooh, I'm not sure.
It's one of our like solvents for something.
I had like furanone or something like that, but I think I remembered it being a 5-membered ring that had the oxygen at the top. And out of these, fructose is a 5-membered ring, correct?
Yeah, lactose would be a disaccharide. Mannose is an isomer of glucose. Sucrose is also a disaccharide. So we could rule out immediately the disaccharides, and then mannose you would have to recognize that would be a pyranose, a 6-membered heterocycle.
Assuming that we're correct with that, which we'll find out in a second.
Nice.
Yes. Okay, fructose, 5-membered ring. It's got that oxygen at the top. Awesome. Okay, next question. Which of the following carbohydrates does not contain at least one glycosidic linkage? Lactose, amylose, mannose, sucrose. So glycosidic linkage, that's when you're linking together just two carbohydrates, right?
Exactly. 2
monosaccharides combined together is a glycosidic linkage. So lactose is... sucrose is. I don't know about amylose, but we know now that mannose is a monosaccharide, therefore it would not.
Yep.
Okay, so mannose. Yes, we got it.
Well done.
Okay, question number 5. The straight chain form of glucose differs from the straight chain form of fructose in which of the following ways? Units of saturation, number of carbon atoms, number of hydroxyl groups, or the type of carbonyl functional group. Ooh. Okay, so the straight chain form versus glucose versus fructose.
Do you remember?
Well, fructose is a 5-membered ring, but I don't know if it's a 5-carbon.
So fructose, I think, is the ketose version of the aldose glucose.
Oh. So it would be the carbonyl functional group.
Exactly.
So the carbonyl functional group, instead of being terminal in an aldehyde formation, it's on whatever you would call the next carbon in.
Yeah, C2.
Okay, yeah, C2 as a ketone.
Yep.
So it should be type of carbonyl functional group. And it is.
Yep.
Okay, it's fructose is a ketone instead of an aldehyde.
Yeah, so carb naming is really fun because it's like super simple and extremely useful. So anything that's a ketone sugar is a ketose. Anything that's like a 5-carbon sugar is a pentose.
Mm-hmm.
Things make intrinsic sense.
Yes. It's kind of like naming in organic chemistry. I thought it was easy.
There are some of your peers that do not agree.
Well, that's why I was employed as an organic chemistry tutor.
There you go.
Making lemonade out of lemons. Okay, which of the following ketoses contain the same number of carbons as glucose? Sucrose, mannose, galactose, or fructose? So this has to be a ketose, which we just learned means the carbonyl is on the C2 carbon instead of terminal as an aldehyde. And didn't we just say that fructose was a ketose?
Yeah.
So this is a very important thing to remember. You want to know about like the isomers of glucose, because those are going to be tested a lot in possibly a discrete question like this. You also want to know some of the basic sugars. I think a good rule of thumb is if it's involved in one of the major metabolisms, you should know about the structure.
Yeah, and that's a really good rule of thumb. You can't have a carb that's any less than 3 carbons. They all of them in the middle that are not a terminal group should have, an alcohol group on it. And then so for the ones I would memorize would be something like glucose, and then on that aldose side, knowing that galactose and mannose are epimers of glucose. Oh, I'm sorry, galactose. Did I say that?
Galactose, mannose, and galactose.
Yep.
They're both epimers of glucose.
Yeah, and then knowing that fructose is just the ketone version of glucose. And they actually convert in solution back and forth.
Oh.
Yeah.
Oh, ketoenol something.
Yeah, that is the way they go back and forth.
Okay.
And I think the keto version would almost be more stable. Because I think aldoses are, it's easier to do chemistry with them, but... Mm-hmm. That's neither here nor there. That's not what they're asking.
We're jumping into organic chemistry, but the answer would be fructose. Yes, and it's correct. Very cool. I liked that. That felt good. Okay, which of the following molecules is the aldose form of fructose?
Beating a dead horse here.
Yeah, glucose. Okay, very cool. That's the right answer. Cleavage of 2 unknown disaccharides is shown by infrared spectroscopy to result in 4 individual monosaccharide molecules, 2 with ketone functionality, 2 with aldehyde functionality. Based on this data, what is the identity of the 2 unknowns? So once again, you got to know these basic sugars. Lactose and maltose, sucrose and sucrose, lactose and sucrose, or maltose and maltose. So maltose is just 2 glucoses together, right?
Yep, I remember that in a kind of silly way. Maltose is like Mickey Mouse ears, all of the M's right there. It's the same circular thing on either side.
And the glycosidic linkage is cis.
Oh, cis? I don't know. Like alpha 1,4 is how we refer to those glycosidic linkages.
Yeah, I don't know, and I'm just trying to make it make sense in my head. But like, I know that whenever they draw like the disaccharide, the bond goes down, then there's an O, and then the bond goes back up, and then there's the other glucose.
Yeah, I don't know. That might be misleading. There's a bond to an O from a carbon, and then there should be another bond from a carbon to that same O.
Yes, but do you know why do they sometimes draw it so that you have like the one monosaccharide, and then an O, and then it goes down to another monosaccharide?
Yeah, so that's the alpha. The alpha would be if the carbon number 6 and carbon number 1 are pointing away from each other. That's an alpha configuration. Mm-hmm. And beta would be the same. So the carbon number 6 is pointing up, and so is the first carbon on the glucose.
So if you had a beta version, that's where you would see that what I'm calling trans.
Yeah.
Where it kind of makes like a down, sideways, and then down.
Yeah.
And if it was alpha, meaning they're pointing in opposite directions, you would go down, oxygen, and then back up.
Yeah, also I really hate that they choose to do kind of a corner, we're all organic chemistry people, and so anytime we see that bend in that line, we think there's another carbon there, which is really misleading for people.
Yeah, that's true.
But anyway, cis and trans we don't use here at all.
Okay, so you're cleaving 2 unknown disaccharides. You get 4 monosaccharides. 2 of them have ketone functionality. two of them have aldehyde functionality. What is the identity of them? So lactose is a combination of glucose and galactose.
Yep.
And then maltose is a combination of glucose. So the first answer is out.
We have 4 aldehydes, 4 aldoses.
Maltose. Once again, you'll have 4 aldoses because it'll all be glucose.
Yep.
Lactose and sucrose. So sucrose is a combination of, is it 2 fructoses?
No, so, and this is a kind of silly way of saying this one as well. I remember sucrose sucks because it's the disaccharide that has one less carbon than the other ones that you should typically remember for your biochemistry classes. So it is, I think, glucose and fructose. And when I say it has one less carbon, fructose is an epimer of glucose, so it still has 6 carbons, but there's one less chiral carbon. So there's 9 chiral carbons in sucrose.
Oh, so in that case, then, if we had 2 sucroses, we would have 2 aldoses and 2 ketoses.
Yeah.
Okay, so I say sucrose, and we got it right.
Well done.
Okay. All right, next question. An enzyme known to catalyze the cleavage of disaccharides is added to a pure sample of an unknown carbohydrate. Infrared spectroscopy on the resulting solution reveals the presence of 2 separate peaks between 1760 and 1665. Oh, God.
Oh, yeah. Back to IR spectrometry.
Okay. Based solely on this data, which of the following molecules most likely made up the original pure sample? Assume that after all cleavage by the enzyme, all carbohydrates are in the straight chain forms. Maltose, fructose, sucrose, or lactose. Okay, so a little bit of memory here.
Yeah.
From organic chemistry, I remember there was one functional group that you could see 2 peaks. And before I say what that functional group is,
Oh, okay.
I'm going to look at these answers. And I'm going to see, does one of these have a specific functional group that the other ones don't?
Okay.
He says, expecting the exact thing that he's implying. Maltose, that's just a what is it? Epimer of glucose.
Maltose would be 2 glucoses strung together in a disaccharide.
Right. Okay. So that's just glucoses, meaning it should. Ooh, but hang on. Oh no. Okay. Oh crap. I might have just. Yep. I worked myself into a corner. Okay. Maltose is 2. So the thing it might have is that ester bond, right? The glycosidic.
Yeah, I
linkage.
think you're overthinking it here. So when throwing it all the way back to organic chemistry, one of the only things that we had to remember was around like 1720 or 1750, there was a carbonyl. So it's telling us that there's 2 carbonyls present, and there you can see them separately, so there probably should not be at the same position. So maybe I've got a disaccharide of like an aldose and a ketose, so they're shifted. One of them is farther right or left, and now I might have talked myself into a corner, but I'm gonna see. Okay, so sucrose is on there.
Oh, it says an enzyme known to catalyze the cleavage of all disaccharides.
Okay, so that's a clue.
Okay, so maltose and sucrose would be broken up into galactose and into fructose. So peaks are at 1760 and 1665. I think this has got to be either a ketone or an ester. I think
you're overthinking. I don't know where ester is, but I know that the only one around like that 1750 would be those giant carbonyl peaks, and that was a huge determining factor in different structures.
Well, if I didn't know that, I could at least rule out it's definitely not an ester because it says that it broke. Well, no, but you still have esters in those. Oh no, if there's an ester in every single sugar, then it's not going to be that.
Yeah.
So it's got to be that double bond to O. Fructose would do it, wouldn't it?
It would give you 1 peak. The ketone of fructose would give you 1 peak.
And sucrose would be the other? Would be, glucose? That's it.
Yep.
Taal confused.
Well, let Small explain. So, starting with step 1, we see immediately knowing that anything from 1760 down to like 1665, you could have carbonyl groups in that range, and those giant ones are like a major determining factor for structure.
Mm-hmm.
And then I knew that if I saw two separate peaks.
That's what I missed.
Yeah, well, I said that.
I just wasn't listening.
That happens frequently. If I see two separate peaks, then I'm not going to have a glucose on top of each other. There's no way that I could determine between them. So if I had something like fructose, which is a ketose, and then glucose, which is my aldose, then I could see two separate peaks that are shifted slightly different based on what's surrounding them.
Right. There's like slightly different chemistry happening, but you're going to get this, like the signal from having that C double bond O is going to be just as powerful, but based on a little bit of the different chemistry going on, they might be shifted slightly.
Yeah.
Okay, so that two peaks between there, that was the real crux, and it was sucrose, because of the peak that's on glucose and the peak that's on fructose would be slightly different. Okay, next question, the last question. A glycogen polymer and an amylopectin polymer, each containing 100 monosaccharide subunits, are cleaved completely by an enzyme. How many individual glucose molecules are created during this process? 25, 50, 10, 10 plus another 0. So it's at 25, 50, 100, or 200. Okay, glycogen and amylopectin, and each one of them has 100 monosaccharide subunits. They're cleaved completely. So we have 100 glycogen and 100 amylopectin. How many individual glucose molecules are created during this process? So we got to know what's the content of glycogen versus the content of amylopectin.
Yeah.
Glycogen's all glucose.
Glycogen is all glucose, but it is not removed as all glucose, and so that is why I am slightly confused at the moment.
What could it also be removed as?
Glycogen is the majority of it is removed as glucose 6-phosphate, and the only time we remove a bare glucose is when we have a branching point, and we have no information here about how many branching points we have.
So here's my turn to say I think you might be overthinking it.
Okay.
Do you know what amylopectin is?
I think it might be a glycogen analog in plants, maybe, that it is basically comprised of glucose.
Okay.
Yeah.
So essentially here we might have two sets of 100 glucose.
Yeah.
Let's try it.
Okay.
Okay, we got it.
Oh, that makes me so angry.
Oh, because it's glucose 6-phosphate instead of glucose?
Yes, that is not the same thing.
Well, it just has a phosphate on it, but it's still glucose. That is the monosaccharide there.
That phosphate on it is that is the reason that we can't export it if there's a phosphate on it. Like, we phosphorylate glucose to keep it within the cell. You know, like it has a big function. It's a big difference than bare glucose.
But you said it yourself. You're phosphorylating what? Glucose. Strong work, gang.